The vibration insulation is shown in this diagram. This is a passive isolation system, and it is used to insulate delicate equipment from unwanted vibrations. So for example, if you want to insulate an electrical monitoring equipment from vibrations present in the floor of an industrial plant, so you can rest it as shown in the figure. So we have the mass right here denoted by M, and its displacement is denoted by y of t. The displacement of the industrial floor is denoted by u of t from some reference frame. We also have the spring denoted by k, the spring coefficient, and we also have the damping coefficient denoted by gamma. So we proceed to the first problem, the first question. Denote by y of t the displacement of the platform from its equilibrium position relative to some fixed frame of reference. Relative to the same fixed reference frame, let u of t represent the displacement of the floor from its equilibrium position. Show that the differential equation for the motion of the platform is y double prime plus 2 zeta omega naught y prime plus omega naught squared y is equal to 2 zeta omega naught u prime plus omega naught squared u, where omega naught, or the natural frequency, is equal to the square root of k over m, and zeta, which is the viscous damping ratio, is equal to the ratio of gamma over 2 square root of mk. So they are dimensionless parameters. So we need to show that this equation is the differential equation for the diagram that I've shown earlier. So in the next slide, I've placed the equation that we need to prove right here as a reference so that we can see it all the time. And I've also placed the substitutions that are mentioned earlier. The substitution for the natural frequency and the substitution for the zeta, or the viscous damping ratio. So first, we're gonna start with the second law of motion. Net force equals to mass times acceleration. We need to know the forces acting on this spring system. So first, we have the displacement y, and this is directed upward. This is the displacement. And we also have the floor displacement, which we assume is directed upward. So if these two displacements are directed upward, then we know that the spring will always oppose the direction of displacement. Therefore, the spring force will be downward, and also the damping force will negate the direction of position. Therefore, the damping force will be going down. The spring force is, since it's going down, it will be negative, and then the spring coefficient k, and then the displacement. What is the displacement? So we have the displacement y, and we also have the displacement u. To get the net displacement, we need to subtract y and u. So that will be y of t minus u of t. Same thing with the damper. It will be negative since it's downward, and the gamma is the viscous ratio, or the damping coefficient rather, times the difference between the velocity of y minus the velocity of u. So this will be the forces acting on the system. So therefore, this is the equation. The net force is negative k times y minus u minus gamma times y prime minus u prime is equals to ma. And distribute, and a can also be denoted as the second derivative of displacement, since a is acceleration. So a is also y double prime. So substituting and then arrange the order, so we have this equation. So next, we will divide all terms by m. So we'll have this equation right here where all terms are divided by m. Now, we're gonna use these substitutions. So we can see that k, or omega naught squared, will be k over m, right? If we square both sides. And consequently, k will be m times omega naught squared. So we have these two new substitutions, or these new orientations of this substitution. So for the zeta, so let's do it right here. I'm gonna substitute k with this k. So we have zeta is equals to gamma over 2 times square root of m times m omega naught squared. So that will be m squared and then omega naught squared, which will be gamma over 2m omega naught. And to isolate gamma over m, we just need to multiply both sides by 2 times omega naught. So this will be zeta times 2 times omega naught is equals to gamma over m. So we have this, and we also have this, gamma over m and k over m. Since k over m is omega naught squared as shown here, and gamma over m is 2 zeta omega naught as shown here, we can now do the substitutions here, 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 and here, which is this. And this equation right here, this equation is what we are asked to prove, or what we are asked to show. So therefore, we solved problem 1. We show that this is the differential equation for this vibration isolation system. So that's it for question 1.